All right, so we are going to start this lesson off by graphing this function. These, if you remember back from middle school, these vertical bars here around x mean absolute value. And when we're talking about the absolute value of a number, it is its distance away from 0. So none of my output values in this case should be negative, because distance is always positive. So here, starting with -4, the distance of -4 from 0 is 4 units, or the absolute value of -4 is +4. Same thing here, this would be 3, this would be 2, this would be 1. 0 is no distance away from 0, so that's 0. And then these are also 1, 2, 3, and 4. And I'm going to graph these points on this graph. So -4, +4, -3, +3, and so on. So if you notice, as we connect these, this is a new graph that up to this point in our math career we haven't seen yet. And it's the shape of a V. So when we're talking about absolute value functions, they will be creating this V shape. So our goal today is going to be able to graph absolute value functions and talk about transformations that have been performed or applied to the parent function, the absolute value of x. So the first thing to talk about, focus this and make it a little clearer. The first thing we're going to talk about is just some basics when it comes to absolute value functions. They do have that V shape that we just saw in that graph that we created. So it's two rays that have been put together. An array is a endpoint with a line that continues in whatever direction. So a absolute value function is two of these put together to create that V. We are going to have a vertex, just like we did with our quadratic functions in Math 1 and Math 2. However, our vertex here, instead of being on that curved minimum or maximum for the quadratic, it will be that very distinct base point in our V. And then these are symmetrical. So everything on the left can be reflected to everything on the right. So we do still have an axis of symmetry, that vertical line that passes through the vertex. So now, looking at our absolute value of x graph, and we're going to look at how we would write this as a piecewise function. And I'm actually going to do this with two different colors. And we're going to start by identifying here, this is our axis of symmetry at x equals 0. So ultimately, we know we have to write a piece for the right for when x is greater than 0. And we have to write a piece for the left where x is less than 0. And our goal is going to be to write this equation and that equation, and then we'll create our piecewise function. So let's start with the one on the right. We'll start there, give our brains a little boost of confidence. So this is a linear function, so I need the slope and the y-intercept, and I'm going to write this in y equals mx plus b form. Well, the nice thing is our x-intercept is 0, so I'm not going to have a b. Well, I am, it's going to be 0, so it's not going to show up in our equation. And our slope is up 1 over 1, up 1 over 1, up 1 over 1. So our m value is 1. So our equation, excuse me, our equation would be just 1x or x, and that's for when x is greater than 0. Let me put a comma in there and be correct with my writing. Pardon me. Same thing with the left-hand side, except my slope is not positive 1, it's negative 1. So this would be negative x when x is less than 0. So remember back to Math 2 when we did reflection in our transformations unit? The lines, other than the vertical and horizontal lines that we would use these y equals x and y equals negative x. Well, these lines themselves are a reflection of each other. So if I were to fold this graph in half like this, you would see that this line, these two lines would line up right on top of each other. Now, in terms of what's happening right here at 0, there's a couple different ways that we could write this. We could just assign one of these two with an equal to in their domain statement, because regardless of which one I pick, ultimately, it's still going to be 0, whether I substitute in here or here. So this is one option. I could just put an equal to under that inequality sign. Our other option, and I'm going to scoot this down just a little bit so I have more room. We could also, when we have our function here, have negative x for x is less than 0, x for when x is greater than 0. Sometimes you will see, instead of just assigning one to the other, we're going to consider this distinct point something totally separate than either one of these two. So it is possible to see an ancillary just point not connected to either one of the two piecewise functions for a very specific x value. So this right here, this part, would graph my vertex here. So that is a different way that you could potentially see the piecewise function written for this same graph. Not that one is more correct or less correct than the other. They're just two different ways to represent the same thing. So the next thing we're going to do is we're going to actually go and look at a transformation in our, oh, and I've already transformed this. Oy vey. Just pretend. All right, so if I'm looking at I'm going to graph our parent function as well. So there's our parent function. I haven't changed anything about it. The first thing I'm going to do is look at this k value and see what happens if I change k. So I'm going to take my slider. I'm going to go ahead and start to change k, and I'm going to make k positive. Well, as I move k up the slider, my graph shifted up. Conversely, if I make k negative, my graph has translated or shifted down. So k, just like in our other transformations, k moves it up and down. Okay. So I'm going to put that back at 0. Now I'm going to go to h. Now I'm going to make h positive. Take a second. Think back to last semester when we had h in our vertex form of our quadratic. What did that do? Well, if h is a positive number, it's moving us to the right. So x minus 5.2. So technically, right now, because this form is x minus h, and h is positive 5.2, it's the opposite of what I would see in my function. And then here, if I had it at negative 5, let's say, this would say x plus 5 because it would be minus negative 5. So remember, these are always the opposite of what I see in my actual function. So it is x minus h, but if h is negative, you'll see plus here. So this one is always the opposite direction. If I see positive here in my function, I've actually moved to the left. And if I see negative here in my function, I've actually moved to the right. Now we're going to look at a. Thinking back to what a did for quadratics, we're going to see if a does the same thing here for absolute value functions. So if I make a larger, it's going to stretch it vertically and make it skinny. If I put a between 0 and 1 and I make it a small fraction, it's going to make it wide. And as soon as I get to a negative number, it also has been reflected, which is the exact same thing we saw in our quadratics. So if it's a small number that's less than 0, it's stretched and it's very wide. If it's a larger number that's greater than 1, it gets skinny. And then if the number is negative, it's been reflected. So coming back here, we're going to actually write this down and formalize it. So A does a dilation. That's one thing A does. If A is greater than 1, that means it's going to be stretched vertically. So we'll have a skinny graph. If our A value is between 0 and 1, it's been compressed which means it's going to be wide. And A also does a reflection if A is negative. So there's two different things it does. It could do a dilation and it could do a reflection. Now remember, H is the one that was funky. If we have X plus H, that means our H is actually negative and it's been translated to the left. And if we see X minus H, H is really a positive number, and we've translated right however many units H is. For K, it is the same. So if we have a positive K value, we've translated up. It's identical to what we did for quadratics. And if we have a negative K, it has been translated down. So our vertex is HK, just like it was for quadratics. And our axis of symmetry is at X equals H. So those are all of the possible transformations that could happen, which again is identical to what it was for quadratics. All right, so taking this into account, let's talk about some transformations. So one thing I see that my A value is negative. So I know it's been reflected and it's going to open down. I know it's going to have a vertical stretch. Because A is bigger than 1. I know it's going to go 5 units. Oops, if I could spell. I know it's going to go 5 units up because 5 is positive. And it's going to go 3 units right because it's the opposite of what I see here. Over here in our next example, it's going to open up because it has not been reflected and A is positive. I know it's going to have a vertical compression or be wide because that's smaller than 1. Oops, spelling. So this is going to be a wide V shape. This would be a skinny V shape. I know we're going to go 2 units down because of our K value. And I know we're going to go 4 units left because of that 4. And I take the opposite. So let's try graphing some of these. I do have included in here for you in the notes some steps that we're going to go through. I'm going to actually show you 2 different ways to do this. And the first thing I'm going to do, I'm going to actually graph for this first one. I'm going to graph the generic parent function here. I'm just going to do a couple just so you can see another way to do this. So in this case, I know that my vertex is 2, -3. So I'm going to go to 2, -3. Here's my new vertex. And there's no vertical stretch or compression because the A value is 1. So I know it's going to maintain this slope of 1 in both directions. So I'm going to go ahead and do my up 1 over 1 for my slope. And there is my new transformed function. Now your other option, which might take you a little bit more time, I could take my parent function, and I know that this is going to shift right 3, down 2, so I could do that with every single point. Or excuse me, right 2, down 3. I was pointing at the right numbers and saying the wrong numbers. Right 2, down 3. So, right 2, down 3. Right 2, down 3. Right 2, down 3. So you could do that for every point, just like we did with our transformations back in Unit 1 of Math 2. So this went right 2 and down 3. So that's option 1, or that's option 1 and option 2 in terms of graphing. Personally, I prefer not to do the extra work and do the transformation of every single point. That's a lot of extra effort. So what I'm going to do is I'm going to do the same thing I did the first time and use the slope to do my compression or my stretch and also a reflection. So this one, here my vertex is 3, 5. Now you'll notice this is the same function we just did when we were talking about our transformations. So it's going to open down. It's going to be a skinny V. And I have my right 3, up 5 already. So I'm going to start with my vertex. 1, 2, 3. 1, 2, 3, 4, 5. And I know that instead of having a slope of up 1 over 1, it's being stretched by 2, and it's opening down. So instead of my first point being here, I have to multiply that by 2 and stretch out my V and make it a skinny V. So that's what the function would look like. One more graphing, and then I'm gonna actually give you one more thing that I forgot to include in the notes that I printed. So this one, I'm going to have a vertex of -4, -2. So let's start with that. I know that there is no reflection, but I know that there is a vertical compression. So it's going to be a wide V. So instead of going up 1 over 1, I have to go up 1 over 2. So I'm going to go up 1 over, up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. So now I have a wider V than I did before. The other thing that I forgot to print out that could potentially come up is writing an equation from a set of instructions. All right, so this one, they gave me some instructions. They're telling me it's reflected and I have a scale factor. All of this deals with my A value. Up 2 tells me K, and left 3 tells me H. So if I was going to write this function, it has to be negative because it's reflected. Then I'm going to have my scale factor. Then I'm going to have my absolute value. H goes inside. And remember, it's the opposite. So if it's left 3, H is -3, which means I do the opposite sign in here. This tells me K is 2 and K is the same. So this would be the function that goes with this set of instructions for our absolute value graph. They could also tell you to write an absolute value function with a vertex at 5, -7. Well, that tells me everything I need to know. In this case, it's not giving me a scale factor. So this is going to be my H value. This is going to be my K value. So I would have f of x equals no A value. It didn't say anything about a stretch. It's the opposite of H. So I'm going to do -5 and then the same as K, so -7.